Now it's time for the payload of the theory of NP completeness. We're going to see some perfectly ordinary problems, not apparently related to computation in any way, that are also NP complete. Of course, we can cover only a tiny fraction of the problems that are known to be NP complete. But the methods, ways of designing reductions, are the things to take away from this discussion. If you encounter a problem in your work and can't come up with an efficient solution, there is a good chance that you can devise a reduction that proves it NP complete. That proof guides your thinking. You need to consider, for example, whether you need to solve the problem in all its generality, or whether a simple or special case would give you what you need. You need to consider efficient algorithms that offer an approximation to what you really want. Without the assurance that the problem is NP complete, you are less likely to want to attempt, or to justify to your boss, taking one of these simplifying steps. But before moving on to reductions that show the problem's node cover and knapsack to be NP complete, we introduce one more nuance into the theory. NP hard problems are those that would be NP complete if only they were in NP, but that are probably or certainly harder than anything in NP. We talk about the tautology problem, which is an example of such a problem, even though it is very closely related to the problem SAT. We are ready to reduce 3-SAT to a number of other problems, thus showing each of them NP complete. These reductions can be directly from 3-SAT or from another problem that we previously proved NP complete. Remember, the key issue is that each reduction must be in polynomial time. However, in most cases, the construction is computationally simple, so as long as the output is of length polynomial in the input, it will be easy to argue that the running time of the transducer is polynomial. Of course, if a problem is NP complete, it must be an NP. Usually this part of the proof is quite simple, since a non-deterministic polytime Turing machine can use its non-determinism to guess a solution in linear time and then check that it has guessed the solution using some polynomial amount of time. However, there are some interesting cases where we can only show a problem to be NP hard, meaning that if it is in P, then P equals NP, but the problem itself may or may not be an NP. A curious example of an NP hard problem is the tautology problem. A Boolean expression is a tautology if it is true for every truth assignment. For example, this expression is a tautology. Every truth assignment makes x either true or false. So one of the first two terms, that is this or that, will have to be true, and therefore the whole expression is true. We don't even need the term y and z. If you look at Cook's original paper on NP completeness, he was really trying to argue that tautologies required exponential time to recognize. Because tautologies are the theorems of logic, that's what logicians care about, not satisfiable expressions. Cook was able to reduce all of NP to satisfiability, but that is enough to show that if there were a polytime algorithm for tautologies, then P equals NP. We'll address this point in a few slides. In fact, there is good reason to believe the tautology problem is not an NP. On the other hand, its complement, the non-tautologies, including those inputs that don't make sense as Boolean expressions, is an NP. We use the non-determinism to get a truth assignment and evaluate the expression in polynomial time for this truth assignment. If the value is false, then the non-deterministic machine accepts its input. On the other hand, if the non-deterministic machine accepts whenever it finds the value to be true, it accepts the satisfiable expressions, not the tautologies. The class of languages called co-NP is those languages whose complement is an NP. For example, we just argued that the tautology problem is in co-NP because the non-tautologies are in NP. Okay, now P is closed under complementation. We didn't prove this exactly, but it is easy to show because if I have a deterministic Turing machine that halts within P of n steps for some polynomial P of n, we can modify it to accept the complement language. Just have the new machine simulate the original. It halts without accepting if the original machine accepts, and it goes to a new accepting state if the original halts. Since the complement of every language in P is also in P, it is surely an NP, That proves the class P is a subset of co-NP as well as of NP. Another important connection is that if P does equal NP, then P also equals co-NP, and therefore NP and co-NP are equal. However, it is possible, but unlikely, that NP and co-NP are the same, but that they are bigger than P. We can prove the tautology problem to be NP hard. For the proof, suppose there is a polytime algorithm for the tautology problem. Then given a Boolean expression E, convert it to not E, which takes only linear time since all we have to do is add not and a pair of parentheses. Now notice that E is satisfiable if and only if not E is not a tautology. So use the hypothetical algorithm for the tautology problem to tell whether or not E is a tautology in polynomial time. Then just complement the answer. That is, say E is in SAT whenever the answer you got is that not E is not a tautology, and say E is not satisfiable whenever not E is found to be a tautology. That would be a polytime algorithm for SAT, which would show P equals NP. That is all we need for proof that tautology is NP hard. Now let's meet a real problem from operations research that CARP proved to be NP complete. A node cover for a graph is a set of nodes of that graph such that every edge has at least one of its two nodes in the set. We need to express the problem of finding the smallest possible node cover as a yes-no problem. We do so by asking whether, given a graph G and an integer k, does G have a node cover of size k or less? This is the formal problem or language called node cover. Notice that if we had a polytime algorithm for the minimization problem, that is, given a graph, find a node cover of smallest size, then we could prove that the formal problem node cover was in P. Just use the hypothetical polytime algorithm to find a smallest node cover, count the number of nodes in the cover, and see if it is at most k. That means that once we prove the formal node cover problem, or the yes-no version of the problem, to be NP complete, we also know there is no polytime algorithm for the minimization version unless P equals NP. Here's an example of a graph. One of the interesting things about NP complete problems, and node cover is one such, is that even small instances of the problem seem hard. So how small a node cover can we find for this graph? Do you see the answer yet? Well, we'll work it out. We have to pick either C or D for our node cover, or else the edge CD isn't covered. We may as well pick C, because C covers every edge that D covers, and more. We also have to pick either A or E, else the edge AE is not covered. But picking C and either A or E does not cover the edge BF, so we need at least 3 nodes in the cover. But here's one example that works. B, C, and E together cover all the edges. Thus, given this graph and the budget k equals 3, the answer is yes. The same answer applies if the instance of node cover in this graph is this graph with a higher budget. However, if we are given this graph with a budget 2 or less, the answer is no. We're now going to prove node cover to be NP complete. Okay, we'll give a polytime reduction from 3SAT. Given an instance of 3SAT, we construct a graph. There is a node for each literal of each clause, so the number of nodes is 3 times the number of clauses. It helps to imagine the nodes arranged in a rectangle, where the columns correspond to the clauses. Each column has 3 nodes, 1 for each of its clauses. There are vertical edges connecting each pair of nodes in a column, and thus there are 3 vertical edges per column. There are also horizontal edges that connect nodes in different columns. 2 nodes are connected if they represent literals with the same variable, and exactly one of those literals has that variable negated. And finally, the budget k is twice the number of clauses, which is also exactly 2/3 of the nodes. So here's an example of an instance of 3SAT with 4 clauses. We'll construct the graph that has a node cover of 8 nodes, if and only if this expression is satisfiable. So here's the column for the first clause. The literals of the first clause are x, y, and z with no negations. So those are the labels of the 3 nodes in this column. And similarly, we construct a column for each of the other clauses. It is convenient that all 4 clauses have the same 3 variables in order, either negated or not, So this graph is going to turn out to be easier to understand than might be the case otherwise. Now we add the horizontal edges. For example, in the top row where all of the x's are, each node labeled x is connected to each node labeled not x. Again, because all of the x nodes line up and the horizontal edges are truly horizontal. In more complex examples they would not be, although they always go between columns. Similarly, we see connections in the second row between nodes y and nodes not y, and in the third row are the edges between z and not z. And the final part of the output is the budget k. Since there are 4 clauses, the budget is k equals twice that, or 8. The first thing to observe about the constructed graph is that a node cover must have at least 2 of the 3 nodes in every column. If it has only 1 node in a column, then the vertical edge between the 2 unselected nodes will not be covered. And if the node cover has 0 nodes from a column, then all 3 edges in that column will be uncovered. But the budget is exactly twice the number of clauses. So if all 3 nodes in one column were in the node cover, then some other column would be shortchanged. It could get only 1 node and we would not have a node cover. The conclusion is that there can be no node cover with fewer than k nodes, and if there is a node cover of exactly k nodes, then these k nodes must be exactly 2 from each column. We're going to show that there is a tight relationship between the node covers and the truth assignments, and this connection goes through the nodes that are not selected for the node cover. That is, a satisfying assignment for the 3-sat instance will yield a node cover if we omit from the node cover one of the nodes from each column that is made true by the assignment. And conversely, a node cover with 2 nodes per column will give us a satisfying assignment by making all the literals whose nodes are uncovered to be true. We'll prove all this in a minute, but first an example. For example, here's the 3-sat instance we saw earlier, and here's the graph with budget 8 that we constructed. Here's a truth assignment. It happens to be a satisfying assignment, so we can pick a node from each column that is made true by the assignment. Here's one such choice. There are others. For example, in the first column we could have picked y instead of x. I claim that if we take the other 2 nodes from each column, we get a node cover. Surely all the vertical edges are covered since we have 2 nodes in each column. But what about the horizontal edges? Suppose we have a horizontal edge, say with x at one end and not x at the other, and neither end is in the node cover. That means both were selected as the literal that made their clause true. But how could that be? They can't both be true in any one truth assignment, so they can't simultaneously make their clauses true. We need to show that what we described is a polytime reduction from 3-sat to node cover. It is easy to see that transducer takes polynomial time. It works clause by clause, generating no more nodes than there are literals. The vertical edges can be generated at the same time, and they number only 3 per clause. The horizontal edges can be generated easily if we list all the nodes labeled by each literal. After seeing all the clauses, we can generate horizontal edges. For each variable x, we look at the list of nodes for literals x and not x. We generate edges for all pairs, 1 from each list. The total number of edges generated is no more than quadratic in the length of the input, and the edges can be generated in constant time each. We also need to show the reduction is correct, of course. That is, if we construct graph G and budget k from the 3-sat expression E, then G has a node cover of size k or less if and only if E is satisfiable. For one direction, suppose E is satisfiable and let A be a satisfying truth assignment. The argument that G has a node cover of size k is really just the argument we gave for our example earlier. That is, we begin to construct the node cover by selecting for each clause of E one of the literals that truth assignment A makes true. We know there is one because A is a satisfying assignment, and the only way to make a 3-sat expression true is to make each clause true. Then the node cover consists of the 2 unselected nodes from each column. Notice that some of these nodes may also have their literal made true by assignment A, but it doesn't matter. The important thing is that the unselected nodes all correspond to true literals. This selection of nodes has exactly k nodes, since k is twice the number of clauses. So if we can prove it is a node cover, then we have shown that G has a node cover of size at most k, in this case exactly k. We claim the nodes we selected include at least one end of each edge, so indeed we have selected a node cover. First, consider the vertical edges. We selected 2 nodes from each column. There are only 3 nodes per column, so only one is unselected. Thus, any edge in that column has at least one selected end. And how about the horizontal edges? Okay, each horizontal edge has ends corresponding to literals x and not x for some propositional variable x. The truth assignment A has to make either x or not x false. Whichever is false could not have been selected as the literal that makes its clause true. Therefore, it is surely selected for the node cover. That means every horizontal edge is covered, and the k-selected nodes do indeed form a node cover. The converse also follows the outline of the proof we gave in our example. So, suppose G has a node cover with k or fewer nodes. Since all the vertical edges must be covered, there must be at least 2 selected nodes in each column, because one selected node can cover only 2 of the 3 edges. We claim that from the nodes not selected for the node cover, we can figure out a satisfying assignment for E. If there is an unselected node corresponding to literal x, then make propositional variable x true in the truth assignment. If there is an unselected node corresponding to literal not x, then make x false. We'll see why this works on the next slide. Well, what could go wrong? We might have made a truth assignment that makes some variable x be both true and false. That is, nodes corresponding to both literals x and not x might have been outside the node cover. But that can't happen because there is a horizontal edge between these 2 nodes, and therefore at least one is in the node cover. Thus, we do have a consistent, satisfying assignment, and the expression E is in 3-sat whenever G has a node cover of size up to k. Now let's revisit our old friend the knapsack problem. We're going to prove knapsack is NP-complete, but it is easier first to reduce 3-sat to a variant of knapsack, which we'll call knapsack with target. That is, given a list of integers L and an integer target k, is there a subset of L that sums to exactly k? Once we've shown knapsack with target NP-complete, we'll reduce it to the real knapsack problem, which is given a list of integers L, can we divide L into 2 parts whose sums are the same? We have to show knapsack with target is an NP, but that, as usual, is an easy argument. Just use the non-determinism to guess a subset of L, then compute the sum of the integers in the guessed subset, and accept if that sum is exactly k. We're going to reduce 3-sat to knapsack with targets, so suppose we have an expression E in 3CNF and a target k. Let E have C clauses and V propositional variables. We're going to think of the integers in the list L we construct as written in base 32. We can write them in binary, so we need 5 characters per digit, but the factor of 5 is of no importance if we are only worried about performing the transduction from 3-sat instances to knapsack instances in polynomial time. The length of each integer will be C plus V, so each integer could be as long as the entire expression E. There will be 3C plus 2V integers. That means the length of the output could be on the order of the square of the length of the input. But that's okay, it's still a polytime transduction as long as we can generate the integers in time proportional to their length, which we can. Here's a picture of some of the base 32 integers we will use, those for the literals. Notice that each digit will be either 0 or 1, but the base is still 32. We need a base that large to avoid carries from place to place when we add integers. The high order V positions represent the variables. We'll have one integer for each literal xi or not xi, and thus there will be 2V such integers. The integer has a 1 in the ith position from the left end of the first V positions if it corresponds to a literal based on propositional variable xi, that is, it's either xi or not xi. The C low order positions correspond to the clauses. The integer for a literal will have a 1 in the position for each clause that it makes true, and all other positions in this integer hold zeros. There will also be 3 integers for each clause. The integers for the ith clause have, respectively, the base 32 digits 5, 6, and 7 in the ith position from the left end. All other positions are 0. So here's a tiny example. There are 2 clauses and 3 variables in this expression, so c equals 2 and v equals 3. Let's number the 3 variables x, y, and z by 1, 2, and 3 respectively, and number the clauses 1 and 2 in the order in which they appear. Let's see the base 32 integers constructed for this example. Okay. First, consider the literal x. There are 3 variables, so the first 3 positions correspond to the variables. X is the first, so its position is at the left end of the first 3 positions. That's here. Thus we see a 1 there and 0 in the first 2 positions. The last 2 positions correspond to the 2 clauses. When x is true, both clauses are made true, so we have 1s in each of the last 2 positions. Now consider literal not x. The first 3 positions are the same as for literal x, but not x doesn't make either clause true, so the last 2 positions are both 0. That is, these. Here are the integers for y and not y. Among the first 3 positions, they both have their 1s in the middle, as they should. Y makes the first clause but not the second true, so it has a 1 in the low order position, and that's the one that corresponds to the clause 1, and it has 0 in the second from last position. These digits are switched for the literal not y, because not y makes the second clause true but not the first. And here are the integers for z. In the 3 high order positions, they each have 1 in the highest position, as that. And like y, z makes the first but not the second clause true, so the 2 low order positions look like the previous 2 integers. That is, these are like those. Now let's look at the integers for the clauses. For clause 1, we have integers with 5, 6, and 7 in the low order position. And for clause 2, we have the same digits in the second lowest position. We'll pick the target as shown. Note that k in base 32 is v1s followed by c8s. Thus, it is easy to write down in time proportional to the length of the input to the transducer. We claim that when we add a subset of the 2v plus 3c integers, there cannot be any carries from one place to the next higher place. We'll see why on the next slide. In the high order positions, only 2 integers have a 1 in any position, so there can be no carries there. For the low order positions corresponding to the clauses, each position has integers with 5, 6, and 7 there. Even if all 3 are in the selected set, that's only 18, not enough. But what other integers could contribute to a low order position? Only the 3 integers for literals that appear in the clause that corresponds to that position. But these 3 integers only have 1 in that position, so the maximum sum in any position is 21. So there are no carries. But we could have made the base 22 instead of 32, but 32 is easier to convert to binary, so we went with 32. The important consequence of no carries is that the target can only be met by making each position in the sum match the corresponding position of the target. We'll see how this connects satisfying truth assignments to knapsack solutions in the next slide. First, consider the high order positions, the positions for the variables. If the sum of a set of integers matches the target, then the sum must be 1 in that position. That means either x or not x is true for each propositional variable, but not both. That in turn means that the selected integers correspond to a truth assignment. Now let's look at the low order positions for the clauses. The target has 8 in that position. We can't have 2 or 3 of the integers that have 5, 6, or 7 in that position. The sum would be too great. The only way we're going to have integers that sum to 8 in position for a clause is if between 1 and 3 of the integers corresponding to the literals of that clause are chosen, and we can use one of the integers 5, 6, or 7 to make up the difference and reach exactly 8. Now we need to prove the construction we just gave works. First, I hope you see how to construct a single integer for the output in time proportional to the n, which is both the length of the input expression e, and to within a constant factor, the length of the integer itself. Since the number of integers is proportional to the number of clauses plus the number of variables, and there can't be more than n variables in an expression of length n, it is also true that the number of integers in the output is at most proportional to n. Thus, the output can be constructed in time on the order of n squared, and the transduction is polynomial time. We need to show it as a correct reduction. As always, there will be two parts. First, we'll show that if e is satisfiable, then there is a subset of integers summing to exactly k. That is, the output instance of the knapsack with target problem has a solution. Then we'll show the converse, that if there is a solution to the output instance, then the input expression is satisfiable. For the first direction, assume e is satisfiable and let a be a truth assignment that makes e true. For a subset of integers, we'll start with the integers that correspond to the literals that a makes true. That gives us the necessary one in the position for each of the variables, that is the high order positions. The integers we selected so far make each clause true, so their sum in the positions corresponding to the clauses, that is the low end positions, will each sum to 1, 2, or 3. So for each clause, add to the set of integers we're choosing the integer that has 5, 6, or 7 in that position, whatever is needed to make the sum be 8 in that position. Now we have a set that sums to 1 in each of the high order positions, that is the positions for the variables, and to 8 for each of the low order positions, that is the positions for the clauses. That sum is exactly the target, so there is a solution to the output knapsack instance. Now we must show the converse. Assume the output instance has a solution, a subset of its integers whose sum is the target. First, look at the high order positions, those corresponding to the variables. The subset of selected integers matches the target, so it has 1 in each of these positions. The only way that could happen is if we select exactly one of the two integers for the variable corresponding to that position. If x is that variable, that means we picked either the integer for x or the integer for not x, but not both. That means we have a truth value for each variable x. If we pick the integer for x itself, then make x true, and if we pick the integer for not x, make x false. Either way, the literal for the integer we picked is true in this truth assignment, which we'll refer to as a in what follows. Now, look at the position for one of the clauses. We discussed earlier that with only 5, 6, and 7 available for a given position, we have to pick exactly one of them if we are to reach 8 in that position. But we can only reach 8 if the selected integers for the variables have among them something between 1 and 3 ones in that position. That means the truth assignment A must make each clause true, and therefore A is a satisfying assignment. We have now proved that when an output instance has a solution, the input instance is satisfiable. That was the second of the two needed directions, so now we know the transduction is correct. The output has a solution if and only if the input is satisfiable. We're now going to prove the original knapsack problem is NP-complete. We'll refer to it as partition knapsack, but it is exactly what we earlier called just knapsack. That is, given a list of integers, can we partition them into two disjoint sets with equal sums? We'll show partition knapsack to be NP-complete by reducing knapsack with target to it. Remember, we already saw that partition knapsack is an NP, but if you forgot, just guess the partition and sum the two sets. Here's the essence of the reduction from knapsack with target to partition knapsack. Suppose we're given an instance of knapsack with target, say the list L and target K. The first thing we need to do is compute the sum S of all the integers. That takes time proportional to the input length n. Now we can make our output, which is an instance of partition knapsack. This output is a copy of the list L followed by 2 or more integers. One of those integers is 2k, that is twice the target, and the other is S, the sum of all the integers on list L. Here's an example of a knapsack with target instance, the list L consisting of the integers 3, 4, 5, and 6, and a target of 7. The resulting instance of partition knapsack has the same integers, then 2k, which is 14 in this case, and finally the sum s of 3 plus 4 plus 5 plus 6, which is 18. This instance of knapsack with target has a solution. We can select the integers 3 and 4 from L. Their sum is the target 7. The output instance of partition knapsack also has a solution. Take the integers in the solution to the input instance, that is 3 and 4, and include the last integer, the sum of all the integers on list L. Notice that both the selected integers, 3, 4, and 18, and the unselected integers, 5, 6, and 14, sum to 25, which means we have a solution to partition knapsack. That turns out not to be a coincidence. Including the integer that is the sum of L always turns a solution to the input instance into a solution to the output instance. We'll see that when we prove the correctness of this polytime reduction. So here's the proof of correctness. First, observe that the sum of the integers in the output instance of partition knapsack is 2 times s plus k. That is, the integers on list L sum to s, and there's another integer s in the output list, so that makes 2s. And then there is an integer 2k in the output list, which makes 2s plus 2k. Therefore, if we are to partition the output list into 2 parts, each part must sum to s plus k. First, suppose the input instance of knapsack with target has a solution. That means there is a subset of L that sums to k. In the output instance, we can pick this subset of L plus the integer s to sum to s plus k. Of course, what remains will also sum to s plus k, so we have a solution to the output instance. And conversely, suppose there is a solution to the output instance. We claim that the two integers s and 2k cannot be in the same partition because their sum is s plus 2k, and that's more than half the sum of all the integers in the output instance, which recall is 2s plus 2k. Now, if the output instance of partition knapsack has a solution, then the subset of L that is in the same partition as the integer s must sum to s plus k. That's half the total. That means the subset of L sums to exactly k. Now look at the input instance of knapsack with target. We just showed that there is a subset of L that sums to k, so this subset is a solution to the input instance. That completes the proof that the input instance has a solution if and only if the output instance has a solution. We therefore have a valid polytime reduction from knapsack with target to partition knapsack, and we now know the partition knapsack problem is also NP complete.